Have you ever tried to build something and realized the pieces just don't fit? Well, the same thing happens with triangles. You can't just take any three lines and make one. There are some really specific rules, and today we're going to break down exactly what they are. Let's jump right in.
Okay, so here's our game plan. We're going to start with the basics, just a simple idea of greater than. Then we'll build up a toolkit with 5 key helping theorems. After that, we'll actually use those tools in a real proof, explore the awesome connection between a triangle's sides and its angles, and finally, we'll hit the big one, the triangle inequality theorem.
All right, first things first. Before we can even talk about triangle inequalities, we need to be crystal clear on what greater than actually means in mathematics. It sounds obvious, I know, but having a rock-solid definition is going to be crucial.
So in algebra, it's pretty straightforward. We say A is greater than B if you can find some positive number, let's call it P, that you can add to B to get A. Just look at the example. 9 is greater than 4. Why? Because you can add a positive 5 to 4 to hit 9. Simple as that.
And you know what? This same idea translates perfectly into geometry. Take a look at this line segment, AC. It's clearly made up of 2 smaller pieces, AB and BC. Since BC has a real positive length, it just makes sense that the entire segment AC has to be longer than just one of its parts, AB. The whole is always, always greater than the part.
So, with that definition in our back pocket, let's stock our toolkit. We're going to look at 5 lemmas. Now, lemma is just a fancy math word for a helping theorem. It's a small proven rule that we can use as a building block to prove bigger, more complex ideas later on. Our first helper theorem is exactly what we just talked about. It just makes it official. The whole line segment is always going to be greater than any one of its individual parts. Easy enough, right? And this same exact logic applies to angles too. If you take a big angle, like angle ABC here, and you split it into smaller angles, angle 1 and angle 2, well, the whole angle ABC has to be bigger than angle 1, and it also has to be bigger than angle 2. Makes sense.
Okay, this next one is really cool. Check out the exterior angle of this triangle, angle 3. This rule says that it is always greater than the 2 interior angles that are not right next to it. So, angle 3 is guaranteed to be bigger than angle 1, and it's also bigger than angle 2.
Now, this rule is super simple but incredibly useful. We all know a triangle's angles add up to 180 degrees. So think about it. If you have one angle that's 90 degrees or more, a right or obtuse angle, the other 2 have to be small acute angles. There's just no other way for it to add up to 180. That means the right or obtuse angle is automatically the biggest angle in the whole triangle. And for our last helper theorem, we're dipping back into algebra. It's the addition property of inequality. It basically says if you have 2 greater than statements, you can just add them up. If A is bigger than B and C is bigger than D, then A plus C is definitely going to be bigger than B plus D. All right, our toolkit is full. We've got our lemmas ready to go. So now let's actually put them to work and see how we can use one of these to solve a real geometric proof. So here's our challenge. We're given 2 pieces of information. Segment AB is longer than segment CD, and segment BC is longer than segment DE. Our mission is to prove that the combined segment AC is longer than the combined segment CE. And here's what that looks like visually. We've got all these points on a line in order, A, B, C, D, E. So we're comparing the length of this piece, AC, with this piece over here, CE.
And you know what? The proof is a beautiful, clean 3-step process. First, we just state what we were given. That's always step 1. Then, for step 2, we use that addition property we just learned. We add the 2 inequalities together. So AB plus BC is greater than CD plus DE. Finally, step 3, we just clean it up. We know from the picture that AB plus BC is the same thing as AC, and CD plus DE is the same as CE. So we substitute, and boom! AC is greater than CE. Proof complete.
Now we're getting to the real heart of triangle inequalities. This is where we answered the big question. Is there a connection between the length of a triangle's sides and the size of its angles? The answer is a huge yes, and it's one of the most fundamental ideas in all of geometry.
This relationship is a perfect two-way street, and it's captured in these 2 theorems which are just converses of each other. The first one says, the longer a side is, the bigger the angle across from it will be. The second one just flips it. The bigger an angle is, the longer the side across from it will be. It's a direct, locked-in relationship. And this example shows it in action perfectly. Take a look. Angle A is 80 degrees, and angle B is only 40 degrees. Well, since 80 is greater than 40, the side opposite the 80-degree angle, that's side BC,
has to be longer than the side opposite the 40-degree angle, which is side AC. Bigger angle, longer opposite side.
This relationship leads to a really practical and kind of mind-blowing consequence. What's the shortest distance from a point to a line? It's always the path that hits the line at a perfect 90-degree angle. Why? Well, think about it. Any other path you could draw from that point to the line would form a right triangle, and that path would be the hypotenuse. And since the hypotenuse is always opposite the 90-degree angle, the biggest angle in a right triangle, it has to be the longest side. So that straight, perpendicular path has to be the shortest.
Okay, we have arrived at the grand finale. This is probably the most famous inequality rule out there. It's the ultimate gatekeeper, the theorem that decides if three side lengths can even form a triangle at all.
So before I just give you the rule, pause and think about this for a second. Imagine you've got three little sticks. Their lengths are 2, 3, and 6. In your mind, can you connect them end to end to make a triangle? What does your gut tell you?
The answer is no, you absolutely cannot, and it's because those numbers violate the triangle inequality theorem. The rule is simple but powerful. For any real triangle, the sum of any two sides must be greater than the third side. In our little puzzle, 2 plus 3 equals 5, and 5 is not greater than 6. The two shorter sides literally can't reach each other to close the triangle.
So to be thorough, you'd have to check all three combinations. But there's a fantastic shortcut. For any side, its length has to live in a specific range. It must be less than the sum of the other two sides, but it also has to be greater than the difference between them.
So I'll leave you with one final thought to put this all into practice. If you have two sides of a triangle, and their lengths are 7 and 12, what is the entire range of possible lengths for that missing third side? Use that shortcut we just talked about to find out. Thanks so much for watching.